capacitors have a very distinct charging and discharging behavior. To charge a capacitor, you simply supply energy to a capacitor, and to discharge it, you simply withdraw this energy from a capacitor. A simple image to visualize this looks like this. You do have a battery which will supply a certain voltage of U0. You do have a switch by which you can close the circuit, and you do have a resistor with a resistance R. So once you close the switch, a current I will flow for a certain kind of time t, and in this kind of formula you can readily extract that the amount of charges which will flow during this time, which is capital Q, will be a representative of how much energy you can basically store. So how does this charging process in detail work? You basically close the switch and the power supply will create a charge separation in the capacitor. This is what you saw before. We will tend to charge one side of the capacitor with a positive charge and one side with a negative charge. So charging this capacitor, which is basically just a separation of charges, happens in a time-dependent flow of current. Current is nothing else but the flow of charges per time. So you're basically just looking at how quickly or how many charges per second flow through your circuit and therefore charge your capacitor. It is important to note that the electrons exclusively flow via the outer circuit. So once the switcher is closed, the electrons can flow in this range here. They can never cross the capacitor in this kind of setup where you supply the voltage with the battery. And at some point you will reach a point where there is no current anymore. This means that all charges are separated and the capacitor is thus fully charged and in a state as we've seen earlier in the schematics where I showed you a fully charged or fully discharged capacitor. Now this charging voltage which you have in your circuit is not equal to this U0. Actually, it's a rather simple formula which you see here, and please don't be too overwhelmed. I just would like to point out a few influences on this voltage here. So just bear with me and have a look at this UC. UC is the charging voltage. The charging voltage, this kind of voltage, has the contribution of U0, so basically the voltage which your battery supplies. And then it is 1 minus exponential function time divided by tau, which is a time constant. The time constant is equal to the resistance multiplied with the capacitance. So basically UC gives you the time-dependent charging voltage. Because your charging voltage is basically your pressure of the electrons to flow through the circuit, you readily see that the more charges you separate in the capacitor, the harder it will be to flow more electrons in the same direction. So this U0 is the maximum voltage, but the charging voltage never actually reaches this value. And you will observe this time constant, which basically determines the charging time of your capacitor. So when your time is equal to this time constant, when t equals tau, the capacitor is charged by 63.2%. This is simply given due to this exponential term here. And you also see that a low resistance R is basically desirable for rapid charging. Because if R here gets smaller, then your time constant gets smaller, and this means you can charge quicker. We can have a look at this in more practice. Here in this graph, you see the charging state in percent on the y-axis and the time you charge on the x-axis. You now see that for low time constants, so for tau equals 0.01 seconds, you will charge up to high charging states very quickly. And the lower you get in your time, the bigger your time constant gets, the more time it will need to fully charge the system. So on the gray curve, we have 0.1 seconds, and we see that it already takes significantly more time to charge. On this orange curve, we have 0.5 seconds, and it takes even longer. And for a time constant of 1 second, we see that after this 1 second, we are in this specific case where t equals tau. So here we have charged around 63%. And this is what I talked about, what I said with this electron pressure to flow. So the more time passes and the more charges you already separated, the smaller this electron pressure to flow will be after all. Value we should have a look at is the charge current, or as I described it here as IC, which is dependent from T. So the charge current is basically the rate now at which the electrons flow. And the charging current is again given by this expression here, which is the voltage divided by the resistance times exponential minus T divided by tau. Not so interesting, the formula itself. I just again want to point out to you what kind of influence factors we have in there. And we will look at these individually in a second. What I want you to note first is that the current can basically jump because it's only limited by the resistance. So if our resistance is very small, we will have a very high current. The electrons or the charges in our circuit will flow very fast if we have a small resistance. So typically you can observe large current peaks which converge to zero over time the longer you charge, because the more charges you separate, the more the system will resist to separate more charges. If you already shuffled a lot of positive charges on one side of the capacitor, a new positive charge does not really want to go there. It will be harder and harder to push it there. But you see, if your time goes towards zero, so if you look at the initial instant once you close this circuit, for t towards zero, this second term here will become simply 1. So in the t going towards zero, you will have a situation where your current is only given by the voltage divided by the resistance. Now let's have a deeper look into what the individual contributions have an effect on your current, on your charging current. So first of all, the effect of voltage. We readily notice that the higher the voltage, the higher the current will be with which you're charging. So you're moving more charges per second, the higher the voltage is. This makes sense because I introduced to you the voltage as kind of the flow of electrons, or the pressure on the electrons to flow in a certain direction. So the more pressure we exert on these electrons, the faster they will flow, or the more charges per second will move. Now the second effect here is the effect of resistance. We've seen that the resistance especially determines how much your initial current will be. And you see here that just by a difference of 2 ohms in the blue curve to 5 ohms on the orange curve to 10 ohms on the gray and 25 ohms on the dark red curve, you see a significant difference in starting current. So this is something which often has to be controlled manually, so you don't have very strong current spikes. And lastly, you have the effect of capacitance. So basically, one of the major parameters when you think about how much energy can be stored. And this is more or less logic that the more capacitance you want to charge, the longer it basically takes. So if you're just charging a capacitor, having a capacitance of 1 millifarad, you will basically have a drop and you will be charged very quickly. In a 10 millifarad situation, you have 10 times as much charges which you can basically separate, and therefore the drop will be lower, and it simply takes you longer to charge up this system. Now, if we look at the opposite process, so the discharging process, we do not need this energy supply anymore. We simply have our capacitor in here, we have our resistor again, and a switch. So if the source is removed and the capacitor is connected to a resistor, which will act as a consumer and a load, we do already have a system which can consume energy kind of once we close the switch. Notice that I'm simplifying here. We're not using any impedance, but we're simply using an ohmic resistor. So what happens now is that the separated charges in the capacitor, they return to their countercharges once you close the switch. Because here you have accumulated charges on one side, which might be positive here, and negative charges here. So they would like to reunite and basically equalize, so you have a neutral situation again. So once the switch is closed, the separated charges will return to their countercharges, again leading to a flow of current because you have moving charges. So the electrons will flow again via the outer circuit to combine with each other, as they can still not recombine over this capacitor. The more charges now recombine with each other, the smaller the electric field will get, respectively, and the smaller, of course, also the stored energy in the system will get. After all, the capacity voltage decreases and eventually approaches a value of 0. Notice, however, that the same formulas which we've looked at before can also be employed for the discharging situation, only with the opposite sign for the current. What we see here is simply that our discharging voltage is basically given as US, so our charging voltage of the capacitor basically times exponential function minus t divided by tau again. And in an infinite case of an infinitely long discharge, we see that our discharging voltage actually formally never really reaches 0. And our discharging current, of course, will have just the opposite sign as our currents flow in the opposite direction. So how does this look if we put this together? So we again have our discharging voltage, which is basically our electron pressure to flow. And we do have our current, which is basically the rate at which the electrons flow. So we close the switch at 0. So before, that means we do have a constant voltage here, because the electron pressure to flow is the same if none of the charges are moving, and therefore the current is 0 because there is no way for the charges to move from one to the other side or to move towards each other. Now, once we close the switch, the electron pressure to flow will rapidly drop. And this is the case because our electrons will start to flow to the other side, and we will compensate positive and negative charges. And this is a typical observation you can make. Of course, the more your current drops, the more your voltage also drops, or the respective other explanation, the more your voltage drops, the more your current will eventually drop. To review this, I would like to point out a few key things about supercapacitors now. Please recall that in an uncharged supercapacitor, in a discharged state, therefore, we have a random ion distribution. We do have a bulk situation here with positively charged and negatively charged ions, so cations and anions, being randomly distributed. If we have a charged state, we do have a separation here with our anions being on the positive electrode and our cations being on the negative side. So the capacitance of a supercapacitor is formed by various individual contributions, as we've seen. And I would like to point out to you again that there are certain transition resistances in the Helmholtz plane and the electrolyte due to the formation of these processes. And you saw that the resistance is one of the factors affecting the charging time and also the charging behavior, as well as the capacitance, where we said that the capacitance is very different to determine in a supercapacitor. So capacitances further away from the terminal, so the terminal being the electrode, and capacitances which are formed by ions which are further away from this terminal, they have a higher time constant, simply because they have higher resistances. They have higher resistances because there's more electrolyte in between them, and it limits the conductivity, of course. So typically supercapacitors have longer charging times, and they also show certain deviation from ideal charging and discharging curves due to this, not only different capacitance contributions, but also due to different time constants during charging and discharging.